My name is Thomas Mitchell, and I'm a PhD student in mechanical engineering at Johns Hopkins University. My collaborators are Vladimir Kim and Michael Kosdan, and here I'll be discussing our recent work, Field Convolutions for Surface CNNs. Many fundamental image processing tasks, such as segmentation, classification, correspondence, and feature matching, are also integral in the context of geometry processing and the analysis of 3D shapes. Drawing on image-based CNNs, point cloud and graph CNNs have been used to process shape data. But point-based CNNs lose effectiveness in the presence of non-rigid deformations, and graph CNNs are sensitive to mesh connectivity, which is usually poor when working with real-world data. Fully intrinsic surface CNNs are agnostic to both isometric deformations and mesh connectivity, but virtually all state-of-the-art methods sacrifice some measure of filter descriptiveness to overcome the lack of a canonical coordinate parameterization on surfaces. The majority of state-of-the-art image, point cloud, and surface CNNs implement convolutions as gathering operations. To understand what this means, let's consider a planar signal G in an arbitrary filter F. Taking the white node to be our key point P, we'll compute the value of the convolution of the signal G with the filter F at the key point P as a gathering operation, an operation where local information is weighted relative to a single coordinate frame. To do so, we weight each neighbor's contribution by the value of the filter at the point corresponding to the relative position of the neighbor in the frame centered at the key point, essentially taking the dot product of the local signal with the filter. Now, by themselves, basic gathering operations aren't rotation invariant as the relative positions of the neighbors transform under local rotations. To address this problem, many successful surface networks and popular feature descriptors such as SIFT and SHOT extend classical gathering operations with directional information. Here, neighboring features are weighted by expressing their relative positions in the frame determined by the direction of the feature at the key point. This construction is rotation invariant, as such transformations preserve the relative orientation of the neighbor's positions and the directional components of the features. Most importantly, the construction is independent of the choice of filter. In terms of CNNs, this means that the operation ensures rotation invariance while allowing the network to learn any filter. Despite these strengths, gathering operations are inherently fragile. To see this, let's consider what happens when the feature field is perturbed due to noise or other artifacts. If the orientation of the feature at the key point changes relative to that of the neighboring features, the value of the convolution changes significantly, as the contribution of each of the neighbors is affected. This demonstrates the fundamental drawback in using gathering operations for spatial aggregations with directional information. The value of the operation at a given point is entirely dependent on a single coordinate frame or feature orientation, increasing sensitivity to noise. To overcome this weakness, existing state-of-the-art surface networks almost universally sacrifice filter descriptiveness. Instead of aligning the positions of neighboring features relative to the orientation of the feature at the key point, HSN significantly restricts the space of learnable kernels to those that commute with equivariant features. DiffusionNet and ACS-CNN sidestep the alignment problem by relating convolution to heat diffusion on manifolds, with the former providing an especially efficient and robust framework for surface CNNs. However, this approach limits these networks to Gaussian or blob-like kernels, which are individually undiscriminating. Similarly, Mesh CNN avoids the problem by defining convolution relative to the representation of shapes as triangle meshes, incorporating invariance to both isometries and similarities, though the kernels are low-dimensional and abstract, with only hyperlocal support. In response, we introduce field convolution, a surface convolution operator on vector fields. This formulation combines intrinsic spatial scattering with parallel transport while placing no constraints on the filters themselves. In terms of CNNs, this means that in principle, field convolutions can learn any filter. Field convolutions commute with isometries and are naturally robust to noise and high-frequency perturbations of the surface. Using simple networks constructed from residual field convolution blocks, we achieve state-of-the-art results on several standard benchmarks in fundamental geometry processing tasks. Field convolution is based on a simple observation. Instead of combining neighboring features with respect to a single coordinate frame at the key point, we have every neighbor describe the position of the point within its own coordinate frame. In other words, neighboring features are weighted by evaluating the filter at the positions of the key point parameterized in the coordinate frames determined by the direction of the features at the neighbors. This is a scattering operation. Weights computed in a single coordinate frame are spread across neighboring points. Unlike gathering operations, scattering operations with directional information are highly stable. If the orientation of the feature at the key point changes relative to that of the neighboring features, or even if it vanishes, it has no effect on the value of the field convolution, since spatial weighting depends only on the orientation of the neighboring features and the relative position of the key point. Similarly, if one of the neighboring features is perturbed, then only its contribution to the value of the field convolution at the key point is affected. If the other features remain relatively stable, the effect of this perturbation is minimized and the convolution also remains stable. In contrast to gathering operations, where the value of the operation at a given point is entirely dependent on a single coordinate frame or feature orientation, scattering operations, like field convolution, spread the influence of the orientation of each feature across its neighbors, making them significantly more robust. Generalizing field convolutions to arbitrary surfaces requires a few small changes, but the underlying formulation remains the same. Here, our features are vector fields, whose value at every point lies in the tangent plane on the surface. Letting the white node be our key point P, we compute the value of the field convolution of the vector field X with the filter F at P by accumulating contributions from the neighboring points. First, let's consider the contribution from the magenta neighbor, Q. The shortest length geodesic from the neighbor Q to the key point P gives us the information we need to define the position of P relative to Q. That is, the length of the curve gives us the distance and the initial direction gives us an angle. Together, these two quantities give us a point in the tangent space at Q representing the position of P, which we can then express in the frame defined by the direction of the feature at neighbor Q. Then, we weight the contribution of the feature at Q by the value of the filter at the transform point. Recall that our goal is to aggregate neighboring features at the key point. To do so, we express the weighted feature at neighbor Q in the coordinate frame at the key point by transporting it along the shortest geodesic such that the angle between the feature vector and the tangent vector pointing along the curve remains constant as the feature travels over the surface. The value of the field convolution at the key point is given by iterating this process over all neighbors and summing the result. Features are weighted by evaluating the filter at the position of the key point relative to each neighbor as seen in their own frames. Weighted features are then transported to the key point and aggregated. The spatial scattering of feature weights is a symmetry invariant, as such deformations preserve the relative orientation of the tangent vector features and the initial directions of the geodesics connecting neighboring points. Critically, this process can be used to evaluate any arbitrary filter. Transport comprises the equivariant component of the convolution, as the geodesics connecting the points are preserved under isometries, so the expression of transport will rotate with the relative positions of the key point and the neighbors. By combining these two operations, field convolutions offer a flexible notion of convolution on surfaces that is highly robust, commutes with isometries, and places no restrictions on the types of filters learned by a network, increasing descriptive potential. Incorporating field convolutions into surface CNNs is simple and straightforward. Typical network inputs or outputs from previous layers are scalar features. To lift scalar features to tangent vector features, one can use either a simple linear layer or a learnable gradient-like operation to ensure equivariance. The lifted tangent vector features can then be passed to a series of FC resonant blocks. These are simply a classical resonant block with field convolutions and consist of two field convolutions, each followed by a nonlinearity and a residual connection between the input and output streams. Afterwards, the vector field features can be projected back down to scalar features, which are then used as predictions or passed to additional layers. For labeling tasks, we use the feature fields to compute echo surface descriptors, which are then fed through an MLP, turning the task from vector field classification into image classification in the final layer of the network. We call this simple, generalizable architecture an FCNet. Despite its elementary construction, we use it to achieve state-of-the-art results in a variety of fundamental geometry processing and shape analysis tasks. To evaluate our method, we compared it against leading surface CNNs on several standard benchmarks corresponding to fundamental geometry processing tasks: shape classification, segmentation, and dense correspondence. The varied nature of the models in these benchmarks in terms of subjects, acquisition method, mesh resolution, and connectivity serves to test both descriptiveness and robustness. We achieve state-of-the-art results in 2 of the 3 tasks and significantly outperform HSN, whose approach is most like our own but defines spatial aggregations as gathering operations. The superior performance of our method is most likely due to the descriptiveness of field convolutions, as in principle they can learn any filter. Other state-of-the-art surface networks, such as HSN and DiffusionNet, perform spatial weighting with either restrictively parameterized or radially isotropic kernels, respectively. That said, these benchmarks have become relatively saturated, are limited in the types of shape data and deformations considered, and aren't well representative of real-world shape data. To better understand the strengths of our approach, we wanted to try something new. In our last set of experiments, we applied our FCNet to the task of feature matching using meshes from the Shrek 19 shape correspondence dataset. Unlike the other benchmarks, we consider this dataset to be extremely challenging, as it consists of noisy, often occluded real-world scans with significant non-asymmetric deformations and topological changes between pairs. We trained our FCNet, HSN, and ACS-CNN to compute compact, pointwise surface feature descriptors between shape pairs and evaluated performance using precision recall curves. Our FCNet achieved the best performance by a significant margin, followed by HSN. The difference is likely explained by the increased descriptiveness of field convolution and its robust formulation as a scattering operation, making it better able to characterize flat, featureless areas such as the palm of the hand, and insensitive to high-frequency perturbations of the surface as occur in the folds of the figurine jacket. Recent spectral-based surface networks such as ACS-CNN and DiffusionNet have significantly outperformed equivariant surface networks in correspondence tasks, due to their ability to easily scale to high resolutions by essentially band-limiting convolutions by working in a low-frequency basis. Here, this strength appears to become a weakness. Spectral decompositions are inherently global, making them less stable in the presence of non-asymmetric deformations, geometric occlusions, and changes in topology between corresponding pairs. Existing surface learning frameworks, including ours, are designed to handle only isometric deformations, and they struggle to analyze real shape data, where the types of deformations are often much more complex. To this point, our current work involves expanding the field convolution framework to develop convolution operators invariant to conformal automorphisms, beginning with Mobius transformations on the sphere.